Good afternoon.
Hello, nice to see you. How are you doing? Let's wait another minute. Maybe someone else will join.
Okay.
Okay, I guess the people will join on the way who is interested. And reminding our previous topic. So last lecture we were discussing magnetic force acting on conductors with some electric current. So we have shown what forces are acting on different segments of electric conductors carrying electric current. Have shown that the net force on a closed loop of electric conductor is equal to 0. And at the same time, with a closed loop, we have certain torque acting on this closed loop with respect to about some axis which goes through the loop. And this phenomena is used quite widely in practical applications. In particular, the most commonly used is electric motors or actuators, where electric energy is transformed to mechanical energy. Also in some measuring equipment. So last time I was describing some electromagnetic system. So probably it would be better to show an image of this to make it more clear. So here you see a schematic representation of such electromagnetic system where we have a permanent magnet in this uniform magnetic field created between the poles of a permanent magnet. We place a coil with number of loops of electric wire through which the measuring current will run. And also there is some shaft attached spring springs which provide some initial torque and keep this arrow attached to the shaft at the initial position at 0, and then when some current runs through this coil, it generates certain torque because of interaction of electric current in the coil with this permanent uniform magnetic field around the coil. And this torque compensates the torque, magnetic torque compensates the torque created by springs. And this arrow attached to the shaft starts to deflect by certain angle, which is directly proportional to the magnetic torque exerted on the coil with measured electric current. So by calibrating this, we can make an ampere meter, which gives us the magnitude of electric current in the measuring system, electric circuit. So since this coil possesses very small internal resistance, it will not create much of voltage drop, and that's why such electromagnetic ampere meter can be quite accurate device for measuring magnitude of electric current. So let me stop sharing this. Today, as I mentioned last lecture, we will discuss one of the very important application of magnetic field, and specifically interaction with electric current and between electric current and magnetic field. In particular, this will be Hall effect. Maybe I will switch now to the our slides where we can write. Oops, sorry, doesn't work. Once more. Okay, now it works. So before we start to discuss in details Hall effect, I would like to focus your attention on one fact. And as you remember, we derived the Ohm's law, which is electric current density is defined as a product of electrical conductivity times electric field in the conductor. So this is a well-known Ohm's law, and usually it's considered in this form. Electrical conductivity is the property of material. We'll define how well this material can conduct electricity. However, if we go a bit deeper, so we can write that this is also equal and express this sigma in more details. So it will be Q N times mu and times E. So in another way, we also have shown this. It could be represented as Q times N times Vd, which is drift velocity. So this product of mu times E is actually drift velocity. And this mu is mobility, so-called mobility of charge carriers. And it is one of very important parameter because it defines how charge carriers can move in the material of the conductor. And concentration of charge carriers is another important feature of the material and defines how many charge carriers are available for carrying electric current. So how many mobile charge carriers are inside the material of the conductor. That's why both of these parameters, concentration of charge carriers and mobility, are very important and are unique features of, quantify unique features of conducting electricity through some certain specific material. So it is very important to know both of these parameters in order to characterize electrical conductors, in particular metals and semiconductors. However, let's say if we have some JV characteristic means we have electric current density versus voltage, and here is some dependence. From this JV characteristic, which we measure experimentally, it is possible to determine sigma, like one parameter, which will be calculated from the Ohm's law. However, sigma contains two parameters and is defined by, let's say, proportional to concentration of charge carriers and mobility of these charge carriers. And we cannot, from one single measurement of current voltage characteristic, determine these two unknown parameters. We can get only sigma, but we cannot say anything about concentration and mobility. Why? Because we could get the same sigma with large concentration of charge carriers and small mobility. Or in the contrary, the same high conductivity can be obtained with small concentration of charge carriers and large mobility. That's why it is impossible to extract the real numbers, like quantities of these parameters. So taking this problem into account, we need to figure out some approach, technique, in order to measure and quantify these parameters. So it was quite a challenging task, but thanks to some findings of Edwin Hall in 1879, this became possible. And what exactly Hall has found is that when we place a current carrying conductor in a magnetic field, certain potential difference is generated in the direction perpendicular to both the current direction and the magnetic field. So this phenomena was called in honor of the person who has shown this. So that's why it's called Hall effect. And let us consider in more details what is this about. So let us consider some piece of segment of electric conductor, which is placed in a uniform magnetic field. So let us show some system of coordinates. Here is x axis, here is y axis, here we have z axis. So magnetic field is oriented along the axis y, and you can mark it as B. Let us delete these parts on top. We don't need them now. Will be more space. So at the same time, there is some electric current flowing through the conductor in the direction of axis X. So we can show here in this direction, we have electric current. So the height of this conductor is D, and you can also define the thickness of this conductor, which is T. So now consider a very general case. We will discuss this step by step, but later. But now we can consider a very general case and assume that we have two types of charge carriers in this conductor. Say we have negative charges and positive charges. So in order to have electric current flowing from left to right along axis X, drift velocities of these charge carriers should be the following. So this is drift velocity of the positive charges, and we remember that for negative charges, the drift velocity vector should be in opposite direction to the direction of electric current, because they are charged negatively. So in this case, drift velocity is oriented in the opposite direction to the electric current. So this is how positive and negative charge carriers are moving in this conductor in order to have electric current I shown along axis X. Now let us consider what will happen with this moving electric charges which are placed in magnetic field. So definitely there will be some magnetic force acting on them, and that magnetic force is defined as the vector product of drift velocity vector and magnetic field vector. So this we remember from previous lectures. And now if we use this left palm rule, we can show that magnetic force acting on the positive charges will be aligned upwards along axis Z. And what is interesting, there will be the same direction of magnetic field force acting on negative charges, because we need to consider the opposite direction of velocity vector for negative charges, and that's why magnetic field force will be acting in the same direction along upwards along axis Z. So what does it tell us? So regardless of the sign of charge carriers which conduct electric current in the, this material, they will be on their way deflected towards the upper edge of this conductor while they are moving in this magnetic field. So both, let's call electrons negative charges, and we can, it's accepted to in the field of semiconductors to use term hole for positive charges is kind of an absence of electron, which is considered as positive charge carrier. So electrons are negative charge carriers and holes are positive charge carriers. So both of these charge carriers are deflected in the same direction to the same edge of the semiconductor or conductor. This we should keep in mind. And now let us consider the case of a metal. In metals, we have only free electrons, which can participate in charge transport. And that's why only negative charge carriers can conduct, like move through these materials. So let's assume that we have metal, only only electrons are moving there. And that what is going to happen? These electrons are deflected towards the upper edge of the conductor. So we can maybe put here some point C, here some point A. And they will be creating some space charge, negative space charge, because of accumulation of many electrons closer in the vicinity of this upper edge of the conductor. At the same time, since we know that conductor should be electrically neutral, there will be some uncompensated positive charge of metal ions, which are fixed in the crystalline lattice of this conductor material in the vicinity of the bottom edge of the conductor. So we will have some excessive negative charge on top, like here, and some excessive positive charge next to the bottom edge of the conductor. And of course, that will create certain potential difference between this point C and point A. And this potential difference will be perpendicular in the direction perpendicular to both direction of electric current along axis Z, along axis X, and also perpendicular to the magnetic field vector, which is aligned along axis Y. So this is actually the phenomena called a Hall effect. So let us share this my screen. Here. Yeah, so this will be the case for metals when we have only negative charge carriers, electrons. Then, as I explained previously, they will be deflected to the upper edge of the conductor, creating some negative space charge and some positive space charge caused by uncompensated positive charges of ions in metal crystalline lattice will remain at the bottom edge of the conductor. So that potential difference which will be created between these two edges, between point C and point A, will create some internal electric field, which is called Hall field, electric field, and there will be some electric force acting on these charges because of the internal electric field perpendicular to their velocity vector. So this deflection and increase of negative and positive space charges at the opposite edges of the conductor will continue until then, when the magnetic force will be compensated by electric force. They are in opposite directions, and once they are compensated, charge carriers will continue to move straight without any deflection. However, there will be some built-in internal electric field, like Hall field, because of this influence of magnetic field. And if the edge of the conductor where charge carriers are deflected has lower potential than the opposite edge, then we consider that this voltage is called Hall voltage between this like potential difference between these two edges will be negative in this case. So this is true for metals, and the same will be true for N-type semiconductors. N-type semiconductors means that we add some impurities, some dopings to into semiconductor material, single crystal or polycrystalline material, and intentionally increase a concentration of one type of charge carriers. So we can have N-type doping when we increase a concentration of electrons, and then we call them majority charge carriers. Means that most of electric current is carried out by mobile electrons in these N-type semiconductors. So if we have such an N-type semiconductor, it behaves in the same way as a metal. We have majority charge carriers electrons, and the effect of external magnetic field will be the same. So the upper edge of the semiconductor will be charged negatively, and the bottom edge of the semiconductor will be charged positively. However, if we have a P-type semiconductor, means a semiconductor where added impurities significantly increase concentration of holes, not like which are positive charge carriers, then we will have a bit different picture, which is shown on this slide. And in this case, holes like positive charges will be deflected towards the upper edge of the conductor, and in the vicinity of the lower edge of the semiconductor, we will have uncompensated negatively charged acceptors, acceptor atoms, these impurity atoms which we add. In order to have electrical neutrality, positively charged holes should be compensated by negatively charged acceptors, those atoms which were added to the semiconductor in order to increase concentration of holes. If we move and create some positive space charge at the upper edge of the semiconductor because of action of magnetic force on mobile holes in this semiconductor, then at the bottom edge of the semiconductor, there will be some uncompensated negative charge created by negatively charged acceptor atoms. And that's, in this case, the upper edge will be at larger potential, at higher potential than the lower edge. And this polarity will be considered as positive. So this potential difference or voltage, Hall voltage, will be considered as positive. So this is how we define the sign of the Hall voltage. And as you may already notice and have this idea that by measuring Hall voltage without dealing quantitatively with the numbers, only by monitoring the sign of Hall voltage, we can already say what is the majority charge carriers in this conductor. it's either electrons, which are negatively charged particles, then the hole voltage should be negative. And it could be holes positively charged. And in that case, our experimentally measured hole voltage will be positive. So taking this into account, we already can tell quite important, provide quite important information about the conductor which we investigate. We can define by which charge carriers the electric current which is flowing through this material is carried by either electrons or holes. So it's either N-type semiconductor or P-type semiconductor. However, it's not the only nice feature of applying experimental measurements of Hall effect, and it can provide much more information when we go dive into the quantitative analysis of these numbers, of these values of the Hall voltage which we can measure. So there are two common techniques, like approaches to measure Hall effect in semiconductors and metals. If we deal with some bulk crystals, as shown here, we can make a sample, a bulk sample with parallel sides and measure, conduct electricity through this bulk sample and measure Hall voltage at its edges. So it's kind of standard approach to do these measurements. However, very often we deal with thin films, and in that case, it is not possible to make bulk samples, specifically when we deal with graphene, which is known to be monoatomic layer. So it by definition cannot be three-dimensional, it's two-dimensional. So in that case, different approach called Van der Waal technique, which allows to make 4 contacts on these films. And then when we conduct current through between 2 of them, we can measure Hall voltage between 2 others. And then we switch conduct current between these 2 and measure Hall voltage between these 2. And by doing this several times in different directions, we can cancel out some parasitic effects and get accurate value for Hall voltage. So this is a very general description of the techniques, experimental techniques and approaches to measure Hall effect. And now we are going to go into the theory of Hall effect and try to understand quantitatively how we can analyze this measured Hall voltage and how can it help us to get the quantities of concentration of charge carriers and their mobility, which is actually the main goal of applying this technique in terms of analysis of conductors and semiconductors. So let us go to a new slide. And as I mentioned before, the deflection of charge carriers doesn't matter so far, like positive, negative, both types of charge carriers will continue until that time when a magnetic force will not be compensated by the induced internal electric force originated by the induced Hall potential difference between the upper and bottom edge of the semiconductor. So what we can write that under steady state conditions, the magnetic force, which is Q times drift velocity times magnetic field, will be equal to, sorry about that, then this will be electric force is defined as a product of electric charge times whole electric field. So the potential whole potential difference, like so-called whole voltage, we will show it just VH, is equal to whole electric field times height of this conductor, which is the distance between the upper and lower edges of the conductor. And in this case, it will be also equal to V d, drift velocity, times B times D. It comes from the previous equation. So now we know that the electric current can be expressed as electric charge times concentration of charge carriers times drift velocity and times area, the cross section of the or the conductor. From here, we can express that drift velocity is equal to electric current divided by electric charge, concentration of charge carriers, and cross-section area. Cross-section area, by the way, in our case for this image which we have here, it will be the height d times thickness t. So it will be d times t. So now we can substitute, instead of this drift velocity, its expression in this equation where we define the whole voltage. So whole voltage, and this is very important to define to derive equation for whole voltage, because whole voltage is the parameter which we can experimentally measure. We have some voltmeter and measure this potential difference. So this whole voltage will be equal to electric current times magnetic field times D divided by Q and A. So here we have electric current divided by area of the cross section, and that is nothing else as the current density. So we can write here J instead of I times B times D divided by Q N. So this is already very important equation. So it gives us the relationship between current density flowing through the conductor, magnetic field, its geometry, like the distance between the edges in the direction perpendicular to both current and magnetic field, and also concentration of charge carriers in this conductor, either electrons or holes. So this can be further written in another form. So that will be J times B times D divided by RH. RH is so-called Hall coefficient. And from here we can show that the Hall coefficient is equal to 1 over Qn. 1 over the product of electric charge times concentration of charge carriers in the semiconductor or metal. Taking into account that charges can be negative and positive, this Hall coefficient can be also positive or negative. And we can express this Hall coefficient based on the measured Hall voltage. We can also define if it's Hall voltage positive or negative, depends on polarity, as we discussed before. And that's why we can write that Hall coefficient is equal to plus minus J times B times D divided by Hall voltage. So here I want to focus your attention. We, in the right side, we have all parameters which can be experimentally measured. So we can measure current density. We can measure magnetic field. So these parameters are constant and we just predefine them when we do experiment. The same stands for the D, which is the distance between edges of the semiconductor or conductor. And that is also predefined by the experiment conditions. And also in the denominator, we have this Hall voltage, which we actually measure experimentally. So during the experiment. And that means that we know and experimentally measure with high accuracy this term, all terms in the right side of this equation. And it gives us the accurate experimentally determined value of Hall coefficient. If that is true, then we know kind of experimentally measured value of Hall coefficient. And we also know that this Hall coefficient is either positive or negative, which tells us already about the majority the charge carriers, their type, electrons or holes, and type of semiconductor we deal with, electron type or hole type semiconductor. And this is equal to plus minus Q divided by N, which is concentration of these charge carriers. So from here, we can easily determine the concentration of charge carriers. And that will be N equal 1 over Q times RH times Hall coefficient. And since if we have negative charge carriers, then it will be negative Q and negative RH. So this negative signs will cancel each out, and we will always get concentration of charge carriers as positive, a number with units of centimeter per centimeter cubic. So usually a charge carrier concentration is measured not per meter cubic, but per centimeter cubic. So it means how many charge carriers we have in 1 cubic centimeter of this conductor or semiconductor. So by measuring experimentally all parameters here, we calculate Hall coefficient. And by using Hall coefficient, we can calculate unknown concentration of charge carriers. This is first very important step, which is required in the analysis of results obtained from measuring Hall effect. And already we got one of the key parameters we want to know. So now there is still remain the mobility of charge carriers, which we don't know. And again, we can write that electric current is equal to Q times N times mu, which is unknown mobility, times electric field in the x direction, that electric field which causes charge transfer, that causes electric current flow, and times A, which is cross section. So this is equal to sigma times EX times A, and sigma is equal to Q N times mu, which is electrical conductivity of the material. So sigma can be determined from the current voltage characteristic. If we measure current versus electric field, which causes the this current, and that is potential difference between the edges of the conductor divided by its length, we can write that sigma is equal to electric current divided by electric field in this direction x and divided by area A. Where let's maybe highlight this, EX is equal to V, potential difference between edges, divided by L, which is length of the of the conductor. So this, just put it here as a reference. So now we know these parameters. We know current, we know electric field in x direction, we know area. So we can determine sigma. And at the same time, we know that sigma is related to the mobility with this equation. So sigma is equal to Q times N times like electric charge times concentration of charge carriers times mobility of these charge carriers. At the same time, the absolute value of Hall coefficient is equal to 1 over Qn. This is what we derived on the previous slide. I take here absolute value. We don't care about the sign at this point. And let's look what will we get if we have a product of absolute value of Hall coefficient and electrical conductivity. So let's say we have sigma times RH absolute value. So instead of sigma, we put its expression. It will be Q times N times mu, and then times Hall coefficient. It will be 1 over Qn. So you see that here we cancel out Q, the product of Qn. We have in a numerator and denominator. And eventually we get only mobility. So means that mobility, which is still unknown parameter, can be determined by the product of electrical conductivity, which we get experimentally from measuring electric current, cross-section area, and electric field along this current direction. All these parameters can be easily experimentally measured, times experimentally the calculated Hall coefficient based on experimentally measured parameters, which we discussed in details on the previous slide. So that means that with this second equation, by combining Hall voltage measurement and current voltage characteristic, we can get unknown parameter, which is mobility of charge carriers. So eventually, we get independently determined concentration of charge carriers and mobility of these charge carriers. We can also do temperature dependent measurements of Hall coefficient and current voltage characteristics. And then we will get these parameters as a function of temperature and learn even more about the properties of this conductor or semiconductor. So that's why Hall effect is a very critical approach and technique, I would say, like state-of-the-art technique, which had found very wide application in field of semiconductor physics, since it allows us to determine two very important parameters which describe electrical properties of any material. And besides the scientific value of this phenomena, it also found a practical application in so-called Hall sensors, for instance, and they are used in cars to monitor the position of shafts and calculate the moment when to provide like electric discharge to ignite the mixture of gas and air, and also can be a much broader field of application of this type of sensors. However, at the end, I would like to highlight another feature which should be kept in mind, that all this discussion was valid for so-called unipolar conductivity, when either we have only electrons, like in metals, or only or majority charge carriers, electrons or holes in semiconductors. So if we have intrinsic semiconductor, means not doped, then we can have both simultaneously, negatively and positively charged carriers, means electrons and holes, and both of them will contribute noticeably in the carrying out the electric current flowing through this material. In that case, in the case of so-called bipolar conductivity, Hall coefficient is equal to this, can be defined by this equation. So here we have P and N, they stand for concentration of holes and electrons, and mu P and mu N stand for mobility of holes and electrons respectively. So in this case, you see that there are two, actually like four unknown parameters in this equation, mu P, mu N, P and N. And that's why we cannot apply this approach which we did before with in case of unipolar conductivity in order to calculate unknown concentration of charge carriers, because here Hall coefficient will depend not only on concentration of one type of charge carriers, but will depend on both concentration of electrons and holes and mobilities of electrons and holes. And in this case, additional measurements are required to deconvolute this, all these unknown parameters. However, this is valid only for the case of bipolar conductivity in intrinsic semiconductors. And very often we deal with either metals or doped N-type or P-type semiconductors when the majority charge carriers are electrons or holes. And in that case, we can proceed with the described analysis of Hall effect and in a quite easy way get accurate quantitative values for concentration of charge carriers and their mobility in the material of our investigation and of our interest. So this is pretty much everything what I wanted to tell you during this lecture about Hall effect, and hope you learned something new and interesting about this phenomena, which is, as I mentioned already several times, is very important in the field of semiconductor physics. So if you have any questions, you are welcome.
Yes, can we return on 79th slide, previous slide?
Okay, sure. This one? Yeah.
Yes, I just, why like the constant RH will be 1 over Qn? Because if we will return, for example, it will be like the product of JBD and Qn.
So let's say if we go to the equation which defines Hall voltage, so we have shown that it's I times B times D divided by QNA. So then we replaced J as a I divided by A. So we have J times B times D, and here in denominator we have Q divided by N. And we, instead of this
Qn, we replaced RH.
Yeah, you are right. You are right. So here should be not in denominator. So it should be RH. So we should have it in numerator. And RH is 1 over Qn. Thank you very much. I made here a mistake.
And so here it will be VH over JBD, yes? The next formula. RH
Yeah.
while plus my. Okay, so I thank you.
Yeah, thank you for following this.
Goodbye.
Bye. Have a good evening and see you on Monday.
Okay, goodbye. Thank you.
Yeah, and if you see some like mistakes on the way, also you can interrupt me and mention, so it will be more efficient approach.
Okay. Thank you.
Good. Have a good evening. Bye.
Thank you. Goodbye.